So I try to continue where I stopped last time. This was, I think, the last slide I put up last time. Trying to wrap up what we did so far. So, what we actually did not do so far. So trying to work with something like a notion of approximation preserving reductions, which I did not yet introduce. I will spend the next slide on it a bit and see how this works. I mean, this was basically our running example, but we looked through some kind of dual problem to total domination called harmless set. And today I will first try to continue this discussion a bit by looking into what has been introduced in the literature as the differential of a graph. You need to know this. I will explain this in a minute to you, and how this kind of works out there as well, basically. So first of all, maybe this thingy that I so far swept under the carpet is some kind of more general notion of reducibility in the sense of a notion of reduction rules also that helps coping with or keeping up with approximation ratios. So if we want to preserve a certain approximation ratio, then we need, as mostly in approximation algorithms, to deal with both transformation of instances and transformations of solutions. So that's what's basically written there in a kind of language that is more or traditionally coming from or inspired by what people in approximation or do or how they write it. So we have a transformation that transforms instances to instances. And, well, then, on the other hand, we need to talk about solutions of these instances and feasible solutions. And we need another kind of way to go from solutions that we found to solutions, found in this world, basically. So we are trying to solve this here, of course. Yeah. And we get some solutions, and we have to map them back to the solutions that we are kind of really interested in, because we want to solve things over here. So, and this should satisfy certain properties. This is written down up here for maximization case that if I'm looking for optimum solutions of values of optimum solutions in, well, where's this living? It's living over here. And then I may add some number A, and that should be not smaller than this optimum solution over here. And vice versa, somehow, if I'm looking into a solution that I actually get here, like this LS, then the solution that I compute from it should also be not too bad in this sense. And if now this AB is kind of as a product at not bigger, not smaller than alpha. No, this way. Sorry, that's written here. So A is less than or equal to alpha times beta, BB, then we can show, or it's easy to observe actually, that when assuming that this is good for an alpha approximation, then this new solution we kind of compute this way, this S prime is also an alpha approximate solution for the original problem. And this kind of thingy we are actually doing, but I won't go into that too much, just to mention this. This is basically in the back of everything. Okay. As I promised, I want to talk a little bit about the differential of a graph. And this notion was actually introduced by Mashburn, Haynes, had it near me. Well, there are two of them, and Slater. And if you look into papers written by this, say, type of graph theorists, like on domination-like problems, you will often find this name. So it's not, they are not kind of arbitrary people there in this game. And so they define the following notion. So first of all, maybe I go to an example to explain it maybe better than just by formulae. Look at these pink guys. They form the set D, say. Now, the red guys are the ones which are neighbors of the pink guys, which are not yet pink. So in this case, it doesn't really matter because no pink vertex is a neighbor of a pink vertex, but still this is important. So these red guys are, in a sense, and that was the original motivation given by the mentioned authors, are, in a sense, somehow the ones which are maybe influenced or conquered or whatever by the pink guys. And the idea is that somehow... Yeah.
I'm
colorblind. Sorry, I didn't know.
I see.
Sorry.
There's like 3 different colors up there.
Yeah, sorry. There are these 3 pink.
I can't see the laser pointer either for the same
Sorry.
I see 3 very light-colored dots. Those, I'm guessing, are pink.
The light-colored ones are probably the ones which I didn't talk about so far.
Okay. So the ones that look blue to me are pink?
Yes, I think so.
Okay. There are 3 bright blue dots which are pink.
Yeah.
Okay.
And then there is another color.
So the red ones then
Yeah.
are all adjacent to pink ones?
Yes.
But there's one in the middle that seems to be red, but it's adjacent to only the...
I kind of say, okay, sorry. This is, if you look down to the right most lower corner, there's a connection at least. There's this what I, okay.
Oh, yes, I see it now.
Okay, I cannot point, or it's pointless to point, but yes. Is it clear? It's okay. Sorry, I didn't know, so I wanted to illustrate, but yeah. Yeah, so once more. So these, now say again pink guys, so they dominate the red guys, so to speak, or may influence them. And the idea of the authors to introduce this kind of graph parameter was to say, okay, somehow I have to first maybe pay some money or whatever to these pink guys in order to become active to influence their neighbors. So it makes somehow sense to say, okay, my actual measure is something like the number of red guys, the 9, so the neighbors of the pink guys, which are 3. So this difference is actually my gain of influence, which I, as an investor, have. And if you want to see it like this, it's also a variation of a profit problem, if you are still aware. In this parameterized game, like 15 years ago, there was this idea of introducing profit problems. So that is also a bit akin to that. Okay, so and having now defined what the differential of a set of vertices should be, I can then say, okay, I'm not really interested in having the differential of a specific set, but I want to maximize this because this is somehow the maximum influence that I can get, or whatever you call this. And so I try to find the D, the set of vertices D, such that its corresponding differential is maximum among all the subsets of V, and this is now the differential of the graph. Yeah?
So if I have a dominating set of size k, it's differential always going to be n minus k?
If I have a differential of size k, then by definition, dominating of size k, then it's by definition, it's kind of influence vertices are just the remaining ones, so that's n minus k. Yes, but there might be bigger ones. I mean, so this is the hook here. So I need not dominate everybody.
So you could have a dominating set where you could have a graph where the optimum dominating set is the set that gives you the optimum differential available.
Yeah, just for a sec. Is this already an example here? I didn't check actually. But didn't we look at this? We did look at it for total domination, yes. I took the same graph, I must say, for laziness. But okay. Yeah, so but yes, these are this is not the same, sorry. But, okay. Let me next introduce, okay, first, okay, I want to tell a story, yes. It must have been 6 or 7 years ago now, that Sergio Bermudo visited me. And so he brought along this graph parameter, and he's into these graph parameters. And so we thought, okay, let's look at it a bit more from this more graph theoretical point of view. And so we got basically what's listed here. So similar results as I told you about this harmless set stuffy last time. So it's kind of, so if I have a graph of minimum degree at least 1, so connected graph, it's stated here. So of a certain minimum order, in this case, in addition, then I can have a lower bound of n over 5 for my differential. If I have, well, it's not quite correct what's stated there. If I have a minimum degree of at least 2, then I have lower bound of 3n over 11, except for some exceptional graphs, which are actually listed here in this little picture. So maybe just to convince you once more about this, or to increase our understanding of this notion. So this, okay, you can. So in this left picture, there's this now light blue, so probably light colored vertex that is somehow the guy that is proving me as a set that the differential of this graph is 2 minus 1, so 1. Okay? And this 1 is not what my bound would give me. Just if you plug in 4 there, then you would have 12 over 11, which is slightly above 1. So therefore, it must be 2. And this is, of course, not, well, met by this graph. And so you can make similar computations for the other examples. And so there are 5 graphs, although you can only see 3. This is because of the last one up there summarizes 3 different things depending whether or not this red dotted edges are present. Anyway, so so this is this kind of result that we got there, and actually we pretty much liked it. And as you can see, it was published with Discrete Math. Some, well, maybe 1.5 years later, something like that, after we found it. But then again, we looked into, more or less coincidentally, into graph parameters which we know actually better, namely Rome domination. So what's Rome domination? I think this is the notion that more of you are familiar with. So we have a so-called Rome domination function, which associates numbers 0, 1, 2 to vertices of a graph. And the following property should be satisfied whenever I assign 0 to a vertex then at least one vertex in its neighborhood should be assigned 2. Okay? And I'm now summing up all these Roman domination function values, and this should be less than a given number k, or I can also phrase this as a minimization problem. Okay, so this is giving me then, taking the smallest value, this graph parameter gamma sub r as a number associated to a graph again. Okay, so this has been studied from 1999 on, I think, in quite a number, maybe 20, 30, 40 papers, I don't know. Also by those guys introducing this other parameter, the differential of a graph. What we didn't observe that immediately either is something which I will come to later, but maybe just a little excursion to why this is called Roman domination first. So there seems to be some connections to some kind of military strategies used by Constantine the Great in the good old Roman times, where, well, this was basically this sort of known world to the Europeans, dominated by the Romans, and this kind of little graph set on laid on top is somehow reflecting major regions in this empire. Sorry? Sorry? Well, it is at least claimed in one of the first papers where they introduced this in 1999. If you, sorry? Excuse me? No, Stewart. I think it was, yeah, some Stewart and somebody else in American Mathematical Monthly somewhere. Yeah. But I didn't try to check out these sources, I must say. So where this really, really comes from, honestly. Sorry? Oh, what was Scientific American? Maybe also that. Yeah, it was at least Stewart. That's what I recall, and something like that. American, yes. Sorry. Thank you, John. Yeah. Yeah. So, and just to bring one connection more, this kind of phase appeared quite often in my town 10 years ago, because there was some kind of festivity associated to Constantine the Great, because he was also one of those Roman emperors who kind of contributed to many of the ruins in Trier, because he chose Trier to be his capital. So he had to erect many of the buildings like his palace. So this is, if you ever came to Darkstuhl, most likely you have seen this, at least from the outside, because it has been now turned into a Protestant church by the Prussians, which means, of course, you cannot visit it at usual daytimes, often enough at least. But still, it's now, in terms of volume, at least that's what I was told at some point of time, in terms of volume, the biggest church in Germany. So bigger than the cathedral in Cologne or something like that. And just another little piece from history. So you might know that the Roman Empire was, say, overrun to some extent by Germanic tribes. And so they didn't really know how to use all these funny stone buildings. So in the end of the day, in the 5th century, something like that, the Franks actually built a little village inside of this former emperor's palace. So it was that big, so that it just fits a Germanic village. Okay, enough of this kind of history. So back to graphs. And this is more abstract map of the Roman Empire. And so now what has this Roman domination function to do with the Romans? Maybe. Some kind of military strategy at least. So place two armies somewhere on one of these main positions. If you want to defend this position, plus being in the position to move one army from that region to a neighboring region without losing control of the region where the army was situated before. That is at least some explanation of what a Roman domination function does. So, for instance, this is what apparently, according to the Scientific American kind of article, Constantine suggested, put two armies here and two armies there, and of course Britain is in danger then. And according to the strategy and according to everything else I've said. Yeah? So the question is, can we do with 4 major armies? I mean, this is of course what was hidden there, in order to defend the empire in the way that I try to explain, and actually this is possible. This is another possible placement of the armies. And now Rome is very central to some extent. So whenever there's any attack on, say, Constantinople, then Rome should, one army from Rome should move there. But the outskirts of the empire, like Britain and Asia Minor, Turkey, are basically defended by itself. So they cannot move. Otherwise, they would leave the space empty, sort of. But staying there means to defend it. That's at least the idea. So this was this notion. And as I said, that is probably much better studied than this notion of a differential that I started out with. But what we finally noticed is, and this is a 5-line proof, basically both things are the same. It's just some Gala identity, as those graph theorists people would call it probably, or something like a dual parameter in the, say, sense of parameterized complexity. So, and the funny thing is, so that paper that I'm mentioning there basically has this one theory, plus a list of maybe 20 to 25 consequences. Basically looking at the previous literature and saying, okay, this was done for Roman domination. If I translate this now into a result for the differential of a graph, then I get this, and what have these guys on the differential of the graph done so far? Oh, that was worse, so now I have something better now for that parameter. And also vice versa. So funny enough, so it basically improves a heap a lot of results in both ways. And also, unfortunately, it was clear then that our result that I mentioned before was obsolete, because basically 3 years ago, from that publication on, Chambers, Kinnersley, Prince, and West published basically the same result, put it this way, in the Simon Journal of Discrete Maths on Roman domination. So that happens, of course. So what can we take from that? Well, maybe also if we think about graph theory, or if we think about approximation, well, this is also not so much common, I would say, claim at least. We should also think about this kind of dual parameterization at some point of time. Because sometimes switching around your mind, turning around your mind helps. So that's basically my message here. And we should have known this actually before, but this was our way to teach ourselves. We also worked on kernelization, so getting something like a 4K kernel. And along the same lines, we could also prove a factor 4 approximation for the differential. But if you recall my previous inequalities, then, well, we might hope for something better. So this 3n over 11, this is a funny expression, but it translates into something better than a factor 4. So this is what I will be talking about now. And I will in particular now describe several reduction rules, because as I said, my whole approach should be something like reduction rule driven. And maybe starting with something which looks funny if you know classical, say, reduction rules in, well, parameterized setting. Because usually, your reduction rules actually reduce the graph, make it smaller. But this first rule, for instance, makes it somehow bigger. We add an edge between two leaves, which are twin leaves. Well, why do we do this? Because of we want to gain on structure. And what's the structure here? Well, I put up at least a couple of times this slide where I say, okay, I have a nice combinatorial result which talks about graphs of minimum degree at least 2. So somehow I have to do this to get a graph of minimum degree 2, and leaves are bad for me. So this is one way to get rid of them. At least if I have 2 of them attached to the same vertex, and just to make sure that we understand this, that these simple rules work. So what would be a strategy also to find an optimum solution for this domination style problem? Well, if I have a vertex where I have leaf attached to them, what should I do? Naturally, I would pick the neighbor of the leaf to put it into dominating set, and in this case, I would put 2 armies on it. And if I don't do this, well, I should, in this case, put 1 army on each of the leaves. That's what I have to do then in order to secure these leaves, sort of. And that's at least as good, so at most it goes. So therefore, can we simulate the same behavior? Well, if I look now in this little triangle, that's resulting, basically the same argument applies as well. So there's not much better I can do that, but putting a vertex, 2 armies on vertex X. So then there are more funny reductions. There are things which we called hairs, which is nothing than a sort of pendant vertex, or pendant edge, so, which is, well, we put a second vertex in between, sort of, so like as in the picture. And we have like 2 of them here, so then we can basically, and this might be here or might be not there, we basically can get away with a single, so it's sort of two leaves there, well, and so forth and so forth. So there are a couple of similar reduction rules which basically lead to or led us into producing this factor 4 approximation that I mentioned before. But when doing these reductions, and they are all these like alpha preserving reductions, then they will give us, and this is another point I want to make once more, additional structure. So to each vertex, at most 1 leaf is or hair is attached, but not both together. And if we remove all leaves and all hairs from G, just to start with. Then the remaining graph, that I call the nucleus in the paper, has minimum degree at least 2. So somehow maybe we can apply our combinatorial thingy, and some more things about the structure of hairs, how they actually interact with others. Okay. Of course, now we are on dangerous ground, because somehow we want to find some solutions for some original problem. Now we are turning it into some graph which is not necessarily related. So now I'm again sweeping lots of things under the carpet. But in the end of the day, what I want to do is basically work on this nucleus and find some approximation there, or even have it like a kernel, but then have some specific rules how to massage this solution into a solution which is valid for the graph that resulted by applying the previously presented reduction rules. So again, this is not really complete here what I present, but gives at least some idea. And finally, this could be put together and to get something like an 11/3 approximation. And here maybe one open question, if you like to put it like this. So there have been better combinatorial bounds. I didn't look them up once more for graphs which have minimum degree of at least 3, and also for 2 connected graphs. And maybe with some more efforts, one can use this for better kernels or for better approximation algorithms. So we didn't venture into that too much, but at least this is one thing you can do. And maybe let's wrap up what we did so far. So we've seen at least some examples where reduction rules could be useful, at least to get some approximation algorithms, especially for maximization problems. And I also think there should be also a nice bridge to parameterized approximation, the area which you might have expected when seeing the title, which I'm not doing here. But as I said, also the classical polytime approximation could be well inspired here, and sometimes really getting, as I also explained with the last examples, the best what we know today. And again, these reduction rules that I showed are always local massage rules which are easy to implement, so that's not a big deal to do this. However, the combinatorial bit that I mostly sketched only could be a bit more complicated. So that's, in a sense, finally often something like finding some greedy solution first, and then doing some kind of local search to massage the solution, and then this satisfies certain properties that basically are the same that are used in the proof to show certain bounds. So that's basically the strategy there. Not so much really doing or redoing the proof that was somehow presented in order to obtain the combinatorial result. So there's a bit different than there, but still that works out. But just to mention this, of course, greedy and local search are 2 classical strategies for approximation algorithms as well, so it's nothing new, but just sort of used in a little bit different way, I would claim. Okay, if you got bored so much in the last minutes, maybe also because I'm always talking about graphs and you're not so much interested in graphs maybe, let me tell you one more problem. That has nothing to do with graphs, rather maybe with some sort of, well, maybe even topology questions, where many things are open. But this has a similar flavor to some extent. Namely, well, who of you know this, so the theorem of Erdős-Szekeres from 35? So that's about convex sets and stuff like that in point sets. Any idea? Erdős, Sekeres. So they proved, using Ramsey's theorem, that whenever you give me a number k, I can tell you a number nk such that whenever I'm given now nk points, and these points might be in the plane or maybe in the three-dimensional space, if you want to have more fun, or even more dimension, doesn't really matter, then I know that there exists a subset of k points that are in kind of convex position. So, they, so there's nothing in, so no point inside, sort of, in the convex hull. So the funny thing about this is, of course, this is also, or could be turned into something like a computation problem, right? I mean, I give you now a bunch of points and number k, and I ask you, well, doesn't there exist some convex set of with k points, sort of? This problem has a kind of funny history. So actually from the 80s on, but that seems to be not really caught so much. It was known that for the plane, this can be done in polytime. And that was kind of generalized in '92 by people like, if I'm not mistaken, Overmars and Berg and Wöginger and so Epstein are all in the same paper, so not sort of unknown names in this kind of area, who basically showed more general things for the plane. And now, I think it's 2 or 3 years ago, at ESA, Christian Knauer and some students of him showed that in 3D, the same problem is NP complete, or NP complete, yeah. And they also explicitly ask, what about if you look at this from a parametrized point of view? Because this Erdős-Sekeres result immediately gives you a kernel, just to make this clear. So you do have a kernel for this. But it seems to be really completely unknown whether there's a poly-size kernel for this, for instance. And I am not aware of any studies on approximation here. Just if you are bored with graphs, this is something you might want to look at. And maybe something like this could be applicable once you got some more nice kernelization. I mean, the kernelization based on Ramsey is nice, but maybe a bit dear. Okay, so just to amuse you a bit with different things, different from graphs. Okay, so the next thing I still want to go on with is, well, admitting to some extent that everything I want to tell you so far as a general message, that reduction rules could be nice for approximation, it's not that new for the approximation guys either. From quite some time, you might have heard this local ratio theorems, local ratio techniques. I'm not going into details here, but just maybe with one example. But the idea is to give very simple approximation algorithms that do actually do some local transformations, and these algorithms are simple to trivial to analyze inductively, and the basic steps can be easily also viewed as reduction rules. So this method is, again, easy to implement, but one of the beauties here, in my regard is at least, that some of the voodoo techniques that approximation guys use, like, okay, now we apply or throw this into our LP machinery, and all of a sudden we get a result, well, which are, in a following sense, not quite satisfactory to me often, at least, because my intuition is not really there. So I rather want to see something going on combinatorially. And this is somehow possible with local ratio. Somehow, as I will explain at least a bit. And something which I will explain next time, self-monitoring features of approximation algorithms. This can be combined with this local ratio stuffy on top, although I haven't seen anything like it before. Anyways, vertex cover. Okay, some of you might have seen this problem already, so I'm not going to define this. But you also know, probably from any kind of class you have taught or taken, that the following naive algorithm gives a factor of 2 approximation for vertex cover, plus you might also know that under a unit games conjecture, this is optimal, which is kind of sad. Anyway, so what the algorithm, take any edge and put both endpoints into the approximate cover and recurse. So this is a kind of local rule. Grab an edge, put both endpoints into the cover, and repeat until basically there are no edges left. Okay, we get a vertex cover, but just by the very definition of a vertex cover, it is clear. For this edge that I picked, at least one of the 2 vertices will be in any optimum cover. Otherwise, it wouldn't be a cover, by definition. So therefore, I'm losing factor 2 if I grab both. So, so this simple thingy, like having a local rule, basically, that manipulates somehow my graph or my instance and tells me what to put into my cover or whatever solution there is basically the gist of this kind of algorithms. And of course, the local ratio theorem, which is a 2-line proof basically, tells you that, okay, when you have rules which satisfy certain conditions, I can quite easily turn this or prove that this is actually giving me a factor of something approximation. So, for instance, here is a quote from Yehuda's paper, 1 for the price of 2, where he formulates this as follows: iteratively pay $2 at most to reduce the total optimum cost by $1 at least, so the rate of payment is no more than twice the rate of the optimum reduction. This implies the total payment approximation cost at most twice the optimum cost. That's all. And surprisingly enough, this very simple idea is quite powerful. So, for instance, feedback vertex set. Well, there's quite some story behind, some improvement also of approximation factors until people got to the factor 2. But this can be done by a similar, simple algorithm with local ratio. And even more, there is a certain type of equivalence between this type of very simple reduction base, if you want to see it like this, local transformation techniques called local ratio, which are of purely combinatorial nature, to things which are usually proved by LP techniques like primal dual schemes. So these are 2 papers which basically tell, okay, at least for a certain type of problems, these approaches are equivalent, yielding the same thing. The point being, of course, that at least if I look at at the problem from more a combinatorial point of view, it's far nicer to see, okay, there's a local operation, I grab something and do something, than to say, okay, now I've thrown it into my LP machinery and I have some dual and primal upper bounds, lower bounds stuff here, and then something results. At least I can see more if I look at the combinatorial thing. Or I think I can see more. Yeah, so this is what I wanted to tell you at least about this, because, as I said, this also basically is the idea of having local transformation rules applied in order to get approximation algorithms finally. So I'd like to stop here this time and continue next time with something which, as I said, more general reduction rooms for approximation, where I also try to sell a bit things what I already mentioned today, like self-monitoring rules, where I actually can let the algorithm itself output an estimate on its approximation guarantee. That's usually far better than I can derive in general terms. So that's the beauty of that, at least for practical purposes, I would claim. Okay, so maybe I really stop here. And of course, I take your questions if there are any, or comments, or whatever. Questions, comments? Everybody tired? Okay, then thanks.